So we're going to move right into energy. And apologies to Al Gore. An inconvenient truth to chemists, because chemists, as I said, pay no attention to energy for the most part. Later on, I'm going to ask you a few questions about how closely you've paid attention to it. I'm going to start with the big picture, because everything has changed. Certainly within your lifetimes, things have changed rather dramatically. Things have changed even more dramatically in my lifetime in terms of energy. Again, we're addicted to fossil fuels, and we don't have good exit strategy out of fossil fuels. This is an enormous problem which you are going to be facing more so in your lifetime. And oh, by the way, fracking in North America is going to give us at least 100 years of natural gas, which is a completely different way to make molecules from natural gas, right, C2 through about C8, than we currently do with petrochemical industry. We're going to talk about oxidation states and how important they are. And again, I don't think most chemists pay attention to the oxidation state of carbon. And then we're going to talk a little bit about strategies. So again, energy requirements recognized. This to me is the forgotten principle. If any in the 12, this is it. And I would say it's really a recipe for mediocrity, because all it says is synthetic methods should be conducted at ambient temperature and pressure. There is so much richness to energy in chemistry that is not in sight in this principle. And so I hope I bring that richness out to you today. Energy is critical to our industry, to the enterprise. Better than 25% or so of energy is, or 25% certainly of cost is energy in the enterprise. How it's used and some effective strategies. So this is the chemical enterprise context, all right? And energy has not been a dominant economic factor. The fact of the matter is that we're really not paying the true cost of energy as a society. And it's been cheap, dirt cheap, for petroleum, for fossil fuels in general, even for nuclear. Even though distillation is the most used separation technique and the most energy intensive, we really don't bear the cost for it. Important point. 2 oil shocks, again, before you were born, major impacts on how things are done. And again, do not underestimate the impact that fracking will have on the energy equation. It's going to change it completely. This is pre-fracking. Okay, it's only a few years old, but it's still pre-fracking. And what it's showing you is this is quadrillion BTUs of energy. So that's a lot of energy. The point to take away from this and other slides is, guess where most of the world's energy is being used? Oil, natural gas, and coal. This one is increasing, this one is decreasing. They're just switching. That's what fracking is doing for us, all right? Hydro and solar. Everyone say we want to go renewable. Folks, they aren't going to cut it for a long time. Don't have the efficiencies, don't have the energy intensity that we need. Every year, the world uses about 1 cubic mile of oil. Okay, and to replace that, this is what we would need to do that. Okay, so 4 Three Gorges dams. I don't think China is ready for that. 104 new coal-fired plants. China is busy building practically a new plant. It's like every month. It's crazy how many coal-fired plants they're building. Wind turbines, nuclear power plants, uneasy existence with those, but I guarantee you that nuclear is going to be in the equation for quite some time to come, whether you like it or not. This is a spaghetti diagram in multiple incarnations, but again, what is trying to show you is petroleum is a huge component of the overall energy use, and again, transportation. So why do I bring that up? Because chemists impact transportation in so many ways. And you don't think about it, but there's so many opportunities from how things get combusted all the way through the materials of designing in cars and other transportation vehicles. The point again I wish to make here is huge amounts in fossil fuels, embedded in fossil fuels. The thing that this does not show that others will at the end is the amount of waste. So in electricity conversion, there's only about 40-some% that is converted into useful energy. And the amount that actually reaches these bulbs here is somewhere on the order of 2% or less. And if you look at the life cycle energy, it's probably a factor of 100 less. So again, mammoth amount of inefficiency in delivering energy. World energy consumption is growing. Non-OECD, that is developing world, it's going to skyrocket. Proven oil reserves, again, and this picture is changing dramatically again because of the existence of light, tight oil, other unconventional oil, natural gas, fields yet to be found. All right, this is where we've been, which is petroleum reserves in all the countries we know and love, and it's going to go down. Don't underestimate economic growth and the importance of energy in economic growth, and also in population. Hugely important. What this is basically saying is that we've got to do something about fossil fuels because we've got this little problem with CO2 and a host of other heavy metals and other issues. What are we going to do to get out of it? There aren't a lot of options. We've got carbon dioxide emissions, and again, CO2, when it goes into water, forms carbonic acids, and we're acidifying our oceans. So, and our lakes and everything else like that. We're damaging the built environment. We're eroding the outsides of our buildings, so on and so forth. Huge issue. Can we do it with biomass? So that's the world biomass, 60 gigatons. Cultivated crops, 6 gigatons. That's projected energy need. We might be able to do it, but that's currently an extremely inefficient way to get to the energy that we need. So I'm going to switch gears and get us back to the way chemists may think about some, with a short digression. So I'm probably scaring everybody by showing this physical chemistry, right? And you all recognize this, right? I see some smiles. Gibbs, Helmholtz, free energy, right? In your education, which part of this equation do you pay the most attention to? Delta H. Both chemists and chemical engineers. Virtually heats of formation, Q, right? So on and so forth. And you play around with temperature, yes. What about this one? Last night, just for fun, looked at a text when I was in graduate school, which was the text to be using to teach general chemistry. Out of 700 pages, there was one page devoted to that term. Delta S, entropy. The world, humans, use delta H. Who uses delta S? Nature. Nature uses entropy. So what I would encourage you to do in the future is think about entropy and how you might exploit entropic chemical mechanisms to do what you do. So how does energy use it? Membrane formations, weak forces, all those things, alignment of molecules. This is what happens, this is what nature does, ends up with very strong bonds. They're all entropically oriented, okay? You don't see a tree doing distillation, right? Doesn't happen. Oxidation states of carbon. Not going to belabor this, but we like methane. It's at C4, right? -4. This is oxidized carbon, carbon dioxide. The point in all this is just to show that to go from oxidation states requires what? Energy, chemical energy, right? Whether it's energy from a plug, or it's chemical energy stored in some way, or it's energy of formation versus oxidation state. Again, we use energy, chemical energy, all the time to make and break bonds. We don't think about it, but we do. And again, this is really matching raw materials with desired product oxidation states. So again, methane is very useful as a fuel. These particular molecules are very useful for other things that we make, like plastics and higher molecular weight polyols and specialty chemicals and so on and so forth. Oxidation states of carbon matter. Where do we get most of these things? Oh, coal, but look, carbohydrates. And Rich is going to be talking about renewables and how the difference in a reduced carbon molecule versus an oxygenated one or a tremendously functionalized one that we find in nature, all of our chemistry is based on petrochemicals. Not all. Sorry to you. Apologies to carbohydrate chemists and to biochemists. But for the most part, the industry is based in petrochemicals. So we don't need to get into there. So solar, long-term energy, factor 5, most accessible, are the highest oxidation state. So that creates an issue for us for creating molecules that we're interested in, because we have to get them to a lower oxidation state. Carbohydrates can be appropriate, but basically we're just not structured to use that to an extent. Nor are we structured to use proteins, and there's a tremendous amount of chemical diversity in proteins. So here are some things now that you'll all recognize. Yeah, sure, we do heating, we do cooling, we do separations, we do electrochemistry, we do filtrations and pumping. Now I'm finally speaking some language you can really bridge to, right? So what I'm going to go through in the time remaining is just some strategies that you can favor. Near ambient temperature and pressure, that's in the principle, right? So extremely low temperatures are not good. Extremely high temperatures are not good. Running things at reflex are not good, and we'll have an exercise about that. And things that are done under pressure are generally not good. Okay, so supercritical CO2 allows us to do some critical reactions, but if we could get out of that, it would be great. Reaction kinetics. I made an allusion to this earlier on. We don't spend enough time thinking about the kinetics of reactions. Again, chemical engineers do that more than chemists. But again, kinetics are extremely important. Consider scale-up issues for heat removal and heat removal both for heating and cooling. Timing of and order of reagent addition. So you can avoid exotherms just by adding things in a different way. And again, most people don't consider that. Quantity and number. Many times, people don't run reactions in a solvent because they're afraid it's going to react, or because, again, they have a literature protocol which says, we used this solvent. And you don't try anything else. So remember I said 6 or 7 stage reaction or steps in a reaction. Many times you can go across 3 or 4 of those steps with a single type of solvent. But again, people don't try it. And so they end up with, rather than having in a 7-stage process maybe 3 solvents or 4 solvents, they'll end up with 10 or 12. There's no reason for it. Number of distillations, again, we like to do things under vacuum because the distillation can be done at a lower temperature, or it can be done more quickly. If we can avoid the solvent or avoid long reflux periods, we should do it. This is the thing I was saying about reflux. Running reaction 5 degrees below. Why do you have to reflux? Do you really have to run it at the temperature of the solvent to get the reaction to go? Have you checked the kinetics to see what it's like 5 degrees below? Believe it or not, what happens when you're running it at reflux? You've got that heat of vaporization. That is the most amount of energy that's required to go from a liquid to a gas. But heating it up is a lot less energy. Distilling substances with large heats of vaporization. So the more polar and the larger the molecule, the worse it is. Separations are huge demand on energy in general, so there's lots of options that you need to focus on to try and get away from doing separations. I'm not sure how many of you know what evaporation is, but micro and nano and ultrafiltration. This is just simply filtering things, and it is many times less energy intensive than holding a solvent at reflux or azeotroping off one solvent to pull in the next one. I mentioned also about alternative technologies. So many times, many reactions don't go because you don't have good mixing. Or you end up with tarring because you're not getting good heat transfer. And all of that could be eliminated if you had the right design of a reactor. That is not a round bottom flask, but something that looks a little different. This is something that I could do a poll. How many of you have been taught design of experiment, statistical design of experiment? Oh, we got one, maybe two. I don't understand why this is not taught routinely. It seems that the world is content to run a reaction with one set of conditions and then just repeat those sets of conditions and never optimizing the reaction. And in many cases, you can run between 8 and, say, 16 experiments and completely optimize across multiple variables and come up with the best reaction conditions. So I heartily encourage you to learn something about statistical design of experiment, because it has a tendency to remove bias from your experimentation and a lot of mistaken conclusions about what works and what doesn't. It's designed for scaled up processes, and this is something that's going to become more important as you get out of academia and into industry if you take that particular route. But multi-phase solvent systems, emulsions is something that increases the amount of solvent exponentially. Runaway exotherms, huge problem. And mass transfer, huge issue. Again, getting the particular molecules close enough to react, that's really what we're trying to do. And that gets back to my question about why reactions are run so dilute. Let's face it, we've got to get the materials close together so that they react. So there's two ways of doing that. One, increasing concentration, and two, mixing, right? How many of you spend a lot of time optimizing concentration of your reactants and your mixing? Probably very few. For the biochemist, we could spend hours talking about fermentations and opportunities for improving fermentations. Ammonia is a big issue in fermentations. You use ammonia in the form of ammonium salts and use phosphate salts and things like that, but we're not at a point where we can do ammonia recycle, and that becomes a huge wastewater problem. pH control is an enormous issue. Carbon sources for feeding your bugs or your, not your algae because they're going to be doing CO2, but in most fungal or microbial fermentations, pH control and carbon sources are extremely important. They invariably take you back to agrochemical, like sugar. So I just want to come out to the macro scale and give you another factoid. Most people think that all of the energy is consumed in running the process. In fact, most energy in R&D organizations, all right, and in most industrial settings is a base load energy. Number one, HVAC, or refrigeration and steam. So again, there's very little you can do from a chemical perspective in the current way in which we make molecules. And I'll just leave it at that. There's lots of things you can do if we tried making molecules in a different way that would change that. But right now, this is where we're at. This is just another depiction of the same kind of thing. The thing to note in this slide in particular is the amount of energy that ends up in losses. All right, transmission losses, boiler and electricity losses, pipes, valves. steam traps, so on and so forth. Tremendous amount of energy that we produce is lost. So think about that the next time you set up your reaction to do a distillation and you put a heating coil around. And I think that I'm getting more than the high sign here, so I have to stop. And you have another activity.